Okay, so I'm just going to do a quick session to show how you'd analyze a more complicated frame. We're not going to do the full lot, otherwise we'll be here forever. We are just going to zoom in. We're going to go from the start to doing this joint here, because for what we're doing, a joint with 1, 2, 3, 4 things happening is as complicated as we're going to get. Okay, and hopefully if you do find a joint where we've got 5 things happening, then you'll be able to just apply these same principles to it. Okay, so where do we start? Well, as ever, we need to start with magic moments. So to do that, we need some dimensions for this. So I'll put some dimensions on and we'll take it from there. Okay, so we just added some quick dimensions there. So we've got 1 meter to the first force. Yeah, so it's 1 meter, so that's going to be 2 meters to the middle. Oh, that means it's going to be 3 meters to there. Oops, easy. 3 meters to there, and then 4 meters to the end. That's right, isn't it? Yes. 1 meter, 2 meters, 3 meters, 4 meters. Excellent. So those are our dimensions. So where do we start now? Well, we draw ourselves a moment diagram to help ourselves out. So I'll put that together. We'll work our way through it. Okay, so I've just thrown that quickly together and I've just put the distances underneath the forces, but obviously that's going to be the same distances that we more carefully measured out there. So for our moments, we assume that our clockwise moments equals our easy for me to say, equals our anti-clockwise moments. So how do we do that? Well, we take moments about a point, and we usually do that about one of the reaction forces. So let's take moments about reaction force 2. And what we've got to remember is the distance from reaction force, take moments about reaction force 1 here. So the distance from reaction force 1 to the point we're taking moments about is 0, and so it drops out of the equation. So we can find reaction force 2 because that's the only thing we don't know. All right, so we identify our clockwise and anti-clockwise moments. So we imagine that we're turning about this point here. Okay, so that would mean that our 20 Newton force would be a clockwise moment, our 30 Newton force would be a clockwise moment, and the only thing pushing in the opposite direction is reaction force 2, and that would be an anti-clockwise moment. So I'll just put some arrows on there to clarify, and those of you paying attention will recognise those arrows from the previous video. The joys of copy and paste. So we've identified our clockwise and anti-clockwise moments. So what we're doing now is we are saying that clockwise moments must equal the anti-clockwise moments, or if you prefer, we can also say that the sum of the clockwise and anti-clockwise moments must equal 0. So there's our clockwise and anti-clockwise moments. So let's take our first moment. So from this point, it's 1 meter. Okay, that's our distance, and our force is 20 newtons. So that's going to be 20 newtons times by 1. And I would like to think that I can just put 20 newtons in, because 20 times 1 is 20, and I don't have to do that in steps. So let's start to build our equation. So we've got 20, that's our 20 newtons times by our 1 meter. Okay, and our next force, clockwise force, is 30, and that's times by 3 meters. Okay, so plus 30 times by 3 meters. Okay, so we can put that in brackets just to keep things, so we can just keep track of things a little bit more. And then on the other side, we have reaction force 2, so that's reaction force 2, and that's times by 4 meters. So that's our equation. That's how our beam balances out. Okay, so we'll just simplify that now, and we'll see where we get to. Okay, I'm not sure whether it's pause or unpause when I talk through the last bits. I'll just quickly recap, and apologies if it's already been recorded. So 20 plus 30 times by 3. So there's our 20 times by 1, our 30 times by 3 meters, and that must equal our reaction force 2 times by 4 meters, which is what we can see there. Okay, so 30 times by 3 is 90, plus 20 is 110. and that must equal 4 times by R2. So we move the 4 across, so we get 110 divided by 4 equals R2. So it's just a simple case then of working that out, and that is our answer. So we get an answer of 27.25, and obviously we stick an N after that because we want to know what we found out. So we found reaction force 2 there. So now we can find reaction force 1, and if you remember previously, we don't have to take moments about R2. We can just say, well, the up forces must equal the down forces, and we can do that quite simply. So 20 plus 30 equals 50. So all we need to say is, well, 50 minus 27.25 is 22.75. So we can just do that quite quickly in our heads. So I'll just fill that information in. So we found our reaction forces quite quickly using magic moments. And our next step then is, as always, to zoom in on a joint. And we can only tackle a joint that has 3 or less things we don't know. And so the only place we can start is at the where R1, the R1 joint or the R2 joint. Because these are the only places where we know 2 things or less. Okay, every other joint, there are 3 things we don't know here. And at this joint, I can't select that, can I? At this joint in the middle, you can't see the cursor, can you? Anyway, at the joint in the middle, there are 1, 2, 3, 4 things that we don't know. So we can't start there. So let's start where reaction force 1 is. And to help me as I do these, I usually number my joints. So I'm going to just quickly do that so we know what we're talking about. And it doesn't matter which way you number your joints. Here I've gone 1, 2, 3, 4, 5, but you could go 1, 2, 3, 4, 5 if you wanted, or it doesn't matter. As long as you're then consistent in your labeling, it doesn't matter. So I'm going to start at the joint that I've labeled joint number 1. So as always, I'm going to draw a zoomed in view, then I can focus on what I'm doing, and then we'll work things out from there. So let me just put together that zoomed in view and we'll talk our way through it. So we've just got a zoomed in view here, just to focus on what it is that we're doing. And that can just be a very quick pencil sketch. So we're going to assume that things are moving away from us if we don't know what they are. So we assume tension until we know otherwise. Okay, let's just make that up. There we go. So we assume tension until we know otherwise. So we've put the arrows pointing away from our joint. So where do we go from here? Well, we want to know what the forces are here and here. So to do that, we apply our equations of equilibrium. We say that the up forces must equal the down forces, and then the left forces must equal the right forces. Or you can do it the other way around. You can say left equals right first and up equals down. It doesn't matter. Sometimes when you do this, there'll be 2 things you don't know, and so you have to move on to the next equation of equilibrium. So let's start by saying up equals down. Well, let's make our lives a bit easier. Let's label these forces so that we know what we're talking about. Yeah, so we've got F1, or if you've done your Bose notation, you could say that that was FAE, or whatever the Bose notation was around that. Or you can call it F1, or you can call it F Fred, or F Tracy, or whatever you like. Again, as long as you're consistent with these things. Okay, so we've got F1, and we'll call this one F2. So we've got F1 and F2. So if we're talking about F1, shall we do the colour coordination thing again? Let's do the colour coordination thing again. We'll do some colour coordination. I'll put some colours on here and we'll use those as we work it out. But we're going to start by doing up equals down. So let's start by doing that. Up equals down. Okay. So we'll do some colour coordination and then we'll start the equations. Oh yes. Okay, so what have we got going up here? We have got R1, that's a nice green arrow, and then we've also got the vertical component of F1. Okay, and if you remember from before, we said that if if we were finding the vertical, we'd be looking at sine, and we move the hypotenuse over, so it's, oops, let's get rid of that. Sine hypotenuse times by sine theta equals the opposite, and that's the vertical component. If we were looking at the horizontal, then we do the same thing as hypotenuse times by cosine theta, and we covered that in the last video. So I'm just going to remember these two equations at the bottom here and there, and I'm just going to dive in with those. So going up then, we have 22.75. Okay, that's so let's make that nice green colour. Whoopsie daisy, just that. Let's make that green. There we go, 22.75, and that must equal. No, sorry, we've got to add plus, and that must equal the vertical component of F1. So that's going to be F1 times by sine, just make that proper, sine 60. And that must equal the forces going down. But there are no forces going down, so that's a big fat 0 there. Okay, so we need to do our colour coordination, don't we? So let's make that a nice red colour, just to keep things together. Right, so what's next? Well, the only thing we don't know is F1. So we can rearrange the equation to find out F1 then. So let's take our 22.75 over to the other side to become minus 22.75, and then we can divide by sine 60, can't we? Okay, so let's do that. So what we'd end up with then would be in a nice red colour in just a second, F subscript 1. Okay, F1. Okay, and then that would equal. What's going on here? Why is it not aligning? Ah, right, okay. Just give me a second. No. There we go. So F1 would equal minus 22.75 divided by sine 60. Okay, so we'll just give that some nice colour. Okay, and that would equal F1, so we can plug that into our calculator and we can find our answer, which is 26.27. So let's just finish this for the sake of completeness. So let's just copy that, shall we? It's going to be quicker, isn't it? F1 equals 26.27, and I'm just rounding up there to 2 decimal places. Okay, and we stick a unit after that, don't we? Because we found out something new and exciting. No, it's a minus sign because we've got a minus there. Okay, don't forget the minus signs, people. So what does the minus sign tell us? Well, the minus sign tells us that instead of it being in tension over here, it's going in the opposite direction and must therefore be in compression. So let's make that so. Yeah, so we update our diagram to reflect the new information. So we know what it equals, yeah, and so we can put that information over here, can't we? Just so we've got everything in one place. And we know it's in compression. Yeah, so like we did before, we would take, well, we know it's in compression, so we can fill in our table. We don't need to take arrows back anywhere. Now we can just say that's in compression because it's minus. Yeah, there's no such thing as a minus force, but we do have forces in the opposite direction. So, oopsie daisy. Okay, right. So that's what we're saying at the end of all that. Yeah, that's what we're saying at the end of all that. Yeah, so a minus sign, so it's in compression. Okay, we don't have negative forces, so as long as we're aware that it's in compression. Okay, so I've just about got time to do the next one. So the next joint we're going to look at now is joint 2. Okay, so again we're just going to zoom in on that joint, and then we'll work our way through it. And things shouldn't get much more complicated than this. This is about as complicated as we're going to get to at this level and at this moment in time. Okay, so if you can do joint 2, you can do anything. After that, it's just repetition, repetition, repetition. Okay, so let's get that set up. There, what am I doing? We've not found F2 yet. We've not found F2. Oh dear, oh dear, oh dear. Right, we'll put that to one side. Let's find out about F2. I'm sure you were shouting that at the screen, saying, "Steve, what about F2?" So let's find F2 before we continue. Let's find F2. You haven't found F2? God, forget me head if it will lose. Right, so for F2, we have to say our left equals our right. That's our second condition of equilibrium. So left equals right. So that's how we're going to start this. So what have we got going to our left? Well, we now know that F1 is going to the left because it's going down towards the joint, and that's new information. So let's run with that. And that's the only thing going to the left, and going to the right we have F2. Okay, so let's have a look and see what that looks like in a formula. Now we know that F1 is 27.27. Okay, and because we're putting our equations on either side of the line, we can drop the minus signs. If we were saying left plus right equals 0, then we'd have to include our minus signs. So let's do this then. So 26.27. Of course, if you're using a calculator, then you'll have hopefully that answer. You'll have that answer in memory, so you can when you come to the calculation, you can do this to much more accuracy. Sorry, this answer you can do it to much more accuracy than I've done. So 26.27 going left, but we need to know the horizontal component of that. So what we need is cosine, multiply that by cosine 60. And that will give us the horizontal component of F1. Okay, and that must equal on the other side F2. Okay, so we'll just highlight those and color coordinate them for your edification. So, oops, daisy. Let's get the 2 in there, and that's red, isn't it? Yes. Okay, so we've got our F1 and our horizontal component of F1 here in red, and then on the other side we've got F2 in brown. So let's continue to do that. So we can calculate then we can calculate 26.27 cosine theta. We can bung that into our calculator and get the correct answer, which is 13.135, and we can see quite clearly then that equals F2. And now we have solved the joint. So now we can go rushing off to the next joint. Right, so, oh, yep, nearly forgot. Always stick a unit after it when we've got an answer. Okay, so there's no minus sign there, so what we're saying then is that F2 equals 13.135, and that is in tension. Okay, so let's just move that out of the way just a little bit there. Tidy that up. Okay, so we've found out everything at this joint. Okay, so now we're going to move on to our second joint, which we've got down here. And what we know then is we know that this line is our F1. Yeah, that's our F1 line. But if we look here, we've got a down arrow there, so there must be an equal and opposite reaction, which is an up arrow at this corner. Okay, so in fact let's color coordinate that, and let's put those arrows on. There. Yeah, because we must have an equal and opposite reaction. So when we zoom in on this corner, then what we've got is we've got an arrow coming that way, and we know that is that is F1, and that is 26.27 newtons. Okay, so there we are. I've put that in red just to keep us on the straight and narrow. So again, we've got two things we don't know, and so we assume that they are moving away from our joint. Ooh, wrong side. No. There we are. We assume that they're moving away from our joint and our intention. So again, we say up equals down. So let's just drag this over here. Might have to move down a little. Let's move down a little bit. Let's make sure we've got space. So we're saying up equals down. So what have we got going up? Well, going up, we've got the vertical component of F1 right here. Okay, so let's bung that in an equation. Dead quick. Yeah. Aligned. So what we're doing then, we've got F1, so 26.27, and it's the vertical component of F1. So again, we're doing sine 60. Okay, so let's again put that in red so we're consistent here. He says, there we go, nice red colour there. Sine 60, that's the vertical component of F1. And is there anything else going up? No, there isn't. That's going down. That's going right, so we don't need that. And that's going down as well. So what we know then is that that's going up. So that must equal, on the other side of our equation, our 20 newtons, okay, plus our vertical component of this force here. And we've not labelled our forces, have we? That's very remiss of us. So let's call these F3. And let's just copy and paste that. And let's call our diagonal there F4. So there's F3 and there's F4. So we want the vertical component of F4. So once more, we're going to be F4, and that's going to be times by sine 60 degrees. Because that's, we can measure, it's going to be 60 degrees. And that's it. So again, the only thing we don't know is F4, so we can calculate F4, can't we? So let's work our way through that. Shall we give F4 a nice colour? Let's give F4 a nice colour. Let's say that nice blue colour. So here we go. Oops, daisy. No. What's going on there? Okay, let's do that separately. F4, nice blue colour, and sine 60 also a nice blue colour, just to help us keep track of what's going on. Okay, so we can bung this into our calculator, 26.27 sine 60, and we get an answer. So let's do that. Let's do that right now. So, oopsie daisy, let me just sort that out. So that's 22.75, 26.27 sine 60 is 22.75, which is in fact R1 there. Coincidence? Who knows? Sine 60, and that equals 20 plus F4 sine 60. So let's take this 20 across, so 20 becomes minus 20. So let's put that in there, minus 20. That doesn't want to be in red, does it? Let's put that as a nice tasteful shade of black. And that must equal F4 sine 60. Okay, so we can move our sine 60 over to the other side, so we divide by sine 60. So let's just copy that, and we'll do that in a new row. Okay, there we go. So in the next row then, we'll bring the sine 60 over, and we'll also subtract the 20 from here, and we'll see what we get. Okay. So all we've done here then is we've just moved that sine 60 across for our next line, and we've subtracted 20 from 22.75. And then we'll find F4. I guess another way we could have done this would have been to move our sine 60 over and cancel them both out. And we should might end up with an answer that's, well, let's see what answer we get. Let's bung it into our calculator and see what we get at the end. Okay, so that equals 3.175 newtons, apparently. So we've just taken that and worked it out as we go. So now, well, all we need to do now, so that's F4, so we know F4, so let's just fill that in and say equals 3.175 newtons. Okay, and that's in tension because it's not a minus sign, so that is still moving away. And then finally we've got force 3. Is that really in tension? Have I messed up somewhere? And so finally we can say left equals right. And so we can say left equals right. And so going left, we don't have anything going left, so that's a big fat 0. And then going right, we have F3, F4, and F1. So that's quite a complicated, well, potentially quite, because it's the horizontal component of F1, horizontal component of F4, and F3. But we know the only thing we don't know there is F3. So I'll just type that out for you. Okay, and so our final equation then, left equals right. We've got our F1 horizontal component in red. We've got our F4. Where's F4 gone? There's F4. We've got our F4 horizontal component in blue. And then you'll notice I've given F3 a nice pinky purple kind of a look. And so we can just type those values into our calculator. 26.27 cosine 60 will give us a number. 3.175 cosine 60 will give us a number. Plus F3. So then all we need to do then is add those two things together, move them all to the side. So F3 is going to be a minus, isn't it? Because we do need to move those to the side. So we'll just do that very quickly. Okay, so just working that out there. 13.135 is 26.27 cosine 60. 1.59 is 3.175 cosine 60. And then in our final line, we add these two together to give us 14.72. And then we move them over to the other side of the equation, gives us minus 14.72. So we know that F3 is minus 14.72 and that is in compression. Okay, and so let's just change those arrows to reflect that. And we are good to go. And that's the most complicated kind of joint that we have to do. Okay, so I'm going to double check my calculations and then I'll upload this, and hopefully that should help you through the assignment. Thank you very much.